Hello, hello. Thank you for joining me back here again. Today we're talking about the integration of transcendental functions. Actually, we've kind of already done some of that. And you can never get enough practice doing U-substitution, but we're going to expand that a little bit with integrating trig inverse functions. So we're going to start with some things you've seen before, get some more U-sub practice, and then move on to trig inverse. So we covered some of this in the last lesson, that the antiderivative of sine is negative cosine, and the antiderivative of cosine is sine. I showed you how to take the antiderivative of tangent and how to take the antiderivative of cotangent. We worked a little bit with e to the x. We worked with ln of x. We didn't work so much with this one, so we'll practice a little bit with that today as well. Probably one of the hardest things to do when doing U substitution is to figure out what U is. You're looking for an inside function. If E is involved, a good place to look for the inside function is in the exponent of E. So let's let U equal 1/2 x cubed. Take the derivative of that. We get du equals 3/2 x squared dx. Well, that's good because we have x squared dx that we still have to take care of. So we'll isolate that, pull the 2/3 out, and we're just integrating e to the u du. Well, that's much easier. The antiderivative of e to the u is e to the u plus c. And of course, we have to bring our 2/3 down with us. And then last step is we need to plug our u back in. So our u goes back in here, and our final answer is 2/3 e to the x cubed over 2 plus c. So for part B, we're raising a constant to a function. We've taken the derivative of that before, and when we took the derivative of that, it was ln of the base, and then repeat the function. The derivative is similar to that, but you repeat the function and then divide by ln of the base. So when we're working on U substitution, we're going to look again in our exponent for our U value. So U equals sine x, du equals, all right, cosine x dx. So we're going to be integrating 2 to the U. So it's 2 to the U divided by ln u plus c, and then we can just plug our u back in. Okay, this one is a little bit tricky, I think. So don't take notes for just a second. Just watch me sort of model a thought process for you. Now, we're often looking for an inside function to be u. So if my u is x to the third, then my du is 3x squared dx. But 3x squared is like, that's not in here anywhere. So that didn't work. All right, so that's okay. We'll just try again. What's a different u we could use? Sometimes I like to look at the entire bottom, okay, to see if that can be u. If we do that, then I have to take, if u equals x ln x cubed, and I take the derivative of that, I get du equals, then, okay, derivative of the first times the second plus derivative of the second, oh wow, times the first. Okay, that is very complicated, so that's not going to work either. So let's try something maybe in the middle. Let's try u being ln x cubed and see where that takes us. And you can start taking notes again if you'd like. So let's let u equal ln x cubed. The derivative of that is 1 over x cubed, and then times the derivative of the inside, which is 3x squared. And then that reduces to 3 over x dx. Aha! Now we're getting somewhere because I've got a 1 over x here, dx. So if 1/3 du equals 1 over x dx, now we are good to go. So pull out the 1/3 and we'll take the antiderivative of 1 over u, which is the ln of the absolute value of u. Make sure you keep your 1/3 and then plug u back in. And you get 1/3 ln of x plus c. Oh, nested natural logs. So fun. Now we have a definite integral, so we actually get to solve this one. We're going to use U-substitution. So once again, if we have an exponent, maybe we try the exponent first to find our u value. So if u equals 3x to the negative 1, where does that take us? The derivative of that is negative 3x to the negative 2, and you can rewrite that and bring the negative 3 over. 1 over x squared. And there we have our x squared, 1 over x squared dx. So now we have negative 1 over 3 e to the u du, but we still need to get our bounds straight. We started with an x bound of 1, so let's plug that in and convert it to a u bound. We get u equals 3. That's our new lower bound. Our old upper bound was 3. And so we'll adjust that to be 1. And then, those are upside down, aren't they? So we'll need to switch those. We need to change 1 and 3, and then that creates a positive here. Okay, now we can finally take the antiderivative. So the antiderivative of e to the u is e to the u. So right now we have 1/3 e to the u evaluated from 1 to 3. Okay, so now we have 1/3 times f of b minus f of a. All right, what are we going to do with this one? Again, you could start with looking at the exponent. So if I have u equals 2x, then du equals 2 dx. And there's just a lot more going on than that. So we're going to have to expand u, and let's make u be the entire bottom of the fraction. If u equals 1 plus e to the 2x, then du equals 2e to the 2x dx. And that we have. So our new problem will be du over u, and now we can change our x bounds to y bounds. So our x bound was 0, plug that in to get a u bound of 2. And then our upper bound was x equals 3, and we'll plug that in and we get an upper bound of 1 plus e to the 6th. It's not pretty, but that's okay. Then we take the antiderivative. So we get the ln of u, I think I should have absolute value brackets there, evaluated from 2 to 1 plus e to the 6th. And plug those in. F of b minus f of a. Now we're moving on to integrals of inverse trig functions. So, in the last chapters, we learned how to go from tan inverse to its derivative, or from sine inverse to its derivative. And it's okay to move back and forth between them. The problem is when you've got something that's not quite simple on the bottom of each of those. But we've got these lovely formulas that we can use, and I'm going to walk you through those. So if you're going to integrate 5 over x squared plus 1, When I first look at that, I think, oh, well, I'll just use U-substitution. And then that doesn't work, right? So I've got to think of something else. Hopefully, in time, you'll recognize, oh, that 1 plus x squared, that's tan inverse. And this is a big one to be watching for. So let's pull the 5 out first. And now this part, see, that just matches here. So that just equals 5 tan inverse plus c. Gets a little bit more complicated in part B because of this 9 right here. So now we'll use maybe a more general version of the formula, and it's helpful to know what's in the A position, what's in the U position. So if you rewrite it, 9 is the same thing as 3 squared. And now I can see that in the A position is 3, in the U position is just x, so that's pretty simple. So du equals dx, so we're taking care of there. And now we can just plug the stuff into the formula. We've got 1 over a tan inverse u over a plus c. All right, let's try some with sine inverse. This one mostly matches, especially on the bottom. The only thing is the 8 that's different, so we'll pull that out to the front. And then we just end up with 8 sine inverse plus c. For part D, of course, we need to use a more general version of this. So let's start with rewriting it so we can see what is in the A position and what is in the U position. And it looks like I dropped my 4x on the top. There we go. All right, so A equals 3, and in the U position is 2x squared. And du is 4x dx, so that's fabulous. And now we could just change everything into the u version and pop it into our formula. Sine inverse u over 3 plus c. But what's u again? U is 2x squared. Oh, I like this one. This one's fun. So we're obviously working with something with sine inverse because they tell us that right here. And in the bottom, that's like the bottom of the derivative of sine inverse. And oh, that's a clue. What happens if u equals sine inverse of x? Then du is 1 over the square root of 1 minus x squared. Aha, that's right here. So really, we're just taking the antiderivative of u, du, which is 1/2 u squared plus c, and plug u back in. You may not like me for this, but it's important that I show it to you. So if you remember completing the square, or hopefully you even just recognize the term completing the square, sometimes we're going to need to use that. So if I look at part A here, the first thing I wonder is, can I use U-substitution? And if I try U-substitution, then when I take du, I get 2x plus 12. Okay, so like there's just too much left over. So that's not going to work. We're not set up necessarily as we look at it for any sort of trig inverse, but let's see what we can do here. So we're going to take the bottom and complete the square on the bottom. So I'm going to take this 37, move it to the outside of a parentheses, and leave myself a space there to fill in. Now to fill in that space, to complete the square, I divide the middle term by 2 and then square it. So 12 divided by 2 is 6. If I square that, I get 36. But if I've added that to the inside of the parentheses, I have to subtract it from the outside of the parentheses. This right here is a perfect square. And then 37 minus 36 is just 1. So factoring this into a perfect square, we get x plus 6 squared plus 1. And now there we have something squared plus 1, and that works into our tan inverse formula. So u equals x plus 6, du equals dx, that's good. So we're integrating du over u squared plus 1, which would be tan inverse of u, or tan inverse of x plus 6 plus c. Okay, let's do another one just so you can get some practice completing the square. So we're going to rewrite this to give ourselves a space to fill in, and then push 25 to the outside. Divide 6 by 2, which is 3. Square it to get 9. If you add 9 on the inside, you have to subtract 9 on the outside. And now we have our perfect square plus 25 minus 9. So on the bottom, x plus 3 squared plus 16. We can still use our tan inverse. It's a little bit more complicated because of that 16. So that means a is 4, right? That's 4 squared. U is x plus 3. Du is dx. So our final answer is 1/4. That's 1 over a. Tan inverse x plus 3 over 4 plus c. I just think it's so cool how this can all work out nicely. It's the fun thing about math. Okay, see you in the next lesson.